Now let's take a look at currents in parallel circuits. So what I've got here is I've got a pump, 13 gallons per second coming out of this pump. Of course, that means that 13 gallons per second has to be going back into this thing. 13 gallons per second coming out, 13 gallons per second going in. That could be considered like the total current or the current through the power supply. And the question is, how does this 13 gallons per second flow into these resistors right here? Now, if you imagine our little senior analogy, where are more seniors going to be able to just get through? The wide door right here or the most narrow door right there? Well, just like seniors, there's more room for stuff, current, water, seniors, whatever you got, to get through this one. So I'm going to say of this 13 gallons per second, I'm just going to say arbitrarily, let's just say that 6 gallons per second go through here. 6 gallons per second. So that goes through there. Now, for these, what's the current going to be through these other ones? Well, now this one's a narrower pipe. So is there going to be more or less going through here? Well, as we discussed before, there's probably going to be less. And I'm just going to make up a number here. Let's just say that 4 gallons per second go through that one. 4 gallons per second going through there. So my question to you is, how many gallons per second must be going through this one? Well, it's a narrower tube, so you might guess it'll be less than either of the other two. But if I've got 13 gallons per second coming out of the pump, I've got to have 13 gallons per second going back in. What does this one have to be? Well, 4 gallons per second and 6 gallons per second add up to 10. This one's got to be 3 gallons per second. So you got the same amount coming out and going in. So these currents all then join together right there and right here. And here's a question for you. So notice they're all going to add back up to this 13 gallons per second going back in there. So to see if you really understand this, what is the current that is passing this point right there? Well, if you say 9 gallons per second, you're right. It's the 3 gallons and the 6 gallons past that point before it's joined by this 4 gallons right there. So similarly, in our parallel circuit, if I've got 13 amps, most of the current is going to go through the lowest resistor. Through this part right here, there's going to be, through this part, 6 amperes rather. 6 amperes through there. And I've got, how did I figure that out? Well, I've got a 12-volt battery here. I just happened to figure out 12 volts across this resistor, as we'll see later. It's 2 ohms, so there's 6 amps through there. This one, there's going to be 4 amperes going through there, 4 coulombs per second. And this one, there's going to be 3 amperes going through. And when they join back together, this is going to be 13 amperes again. And how much current passes this point? If you said 9 amperes, you'd be right. So, in general, for parallel circuits, most current goes through the lowest resistor. Just like in a pool, the widest hole, if you punch a bunch of holes in a above ground pool, the widest hole, that's going to be where most of the water flows out. And the total current is the sum of the individual branch currents. And the way we write that is I total is just equal to I1 plus I2 plus I3, where I1 is the current through R1, I2 is the current through R2, I3 is the current through I3, dot, dot, dot. So it's like a bunch of little creeks like this adding up to a big river flow. Creeks feeding into a river is what this is very much like.